p, right? So the speed of the man is actually this distance right here changing, and it's growing, isn't it? P is growing. So dp dt is 7, right, feet per second. What do we want? ds dt, exactly. We want to know how fast that shadow's moving. ds dt at, good? At what's 12? At p is 12. Good. We want to know how fast s is growing at exactly the moment that that p, that distance, is 12. Yeah? Any questions? I think we've got everything we need. I mean, in terms of like the drawings and what we're given and what we want. The next thing is an equation. And what variables do we have to connect together? P and S. Got to connect those together with any equation you can come up with, but it has to be based on this picture, not this picture. I'll give you a moment to look at that. Anybody see anything? Any relationships here?
Since the triangles have the same angle, is it just like a scaling type of thing? You increase it by a specific amount, all the sides increase by the same amount?
So you're seeing two triangles, right? Is that you're seeing two triangles and that they are very much related to one another. They share the same angles.
Yeah.
Right? So that is the correct way to go. But let's eliminate why we're not thinking Pythagorean here and why we're not thinking like sine or cosine or tangent. So why not Pythagorean? Yeah, these are, look, this P is not on a triangle, right? It's part of this right here, right? So you can't do Pythagorean with P. S you could do Pythagorean, right? Here in the 20, S squared and 20 squared equals that squared. But see, this we haven't even labeled, and we better not throw a variable in here now because then we're going to have a variable that we don't know anything about, right? So this is not going to go any way that we've done before. The thing you have to see here is what we call similar triangles, all right? So before I get to the equation, let me describe what I'm talking about. We have a big triangle, so wait on this. We have a big triangle, 20 and S, right? That's that big outer triangle. Then we have a smaller triangle. I'm referring to this one right here, this triangle right here. See that? Now this side is 6 because that's the man's height, right? What is this side? What is the length of this side right here?
It's
S minus P, right? It's whatever that distance is, S, take away that distance, and that gives you that distance. So this is S minus P. Now these two triangles have a very important property. First, they both have right angles here, right? That's these two right angles, there and there. But the critical part of this is that they both share this angle. That angle, whatever it is the same on both of those triangles, isn't it? Yes? Because this angle makes up the big triangle and this angle makes up the small one. So those two angles are the same. So if they both have a 90 and they both have this angle the same, then what can you tell me about these two angles? They have to be the same, right? I don't know what they are, but they have to be the same because if two angles of a triangle are the same, then the third angle has to be the same because they have to add up to be 180, right? So whatever this angle is, it's the same here. Have y'all seen that notation before with the angle with the line through it? It's just to distinguish angles from one another. These two are the same because they both have one dash. These two are the same because they have two dashes. That means these two triangles are what we call similar. Similar triangles. And there's an important property about similar triangles that you need to know in order to complete the problem. And that is this. I'm going to say it verbally and then I'll say what it actually is. Whenever you're dealing with similar triangles, that means corresponding sides are congruent, or the ratio of corresponding sides are equal. Okay, what does that mean? It means that if you take 20 and divide by s, you should get the same thing as taking 6 and dividing by this. Or if you do 20 and divide by 6, it should be equal to taking the s and dividing by this. Or you could say s divided by the 20 is equal to the s minus p divided by the 6. You can set up any ratio you want as long as they are corresponding sides. Understand? So I'm using that now, and now I'm going to do this. I'm going to create this setup. This divided by this must be equal to this divided by this. I'm choosing to do it that way because I want to keep my variables in the numerators of the fractions. So I'm going to say s over 20 must be equal to s minus p over 6. I am guaranteed that this is true because these are similar triangles. That ratio, these ratios have to be equal. And if I do that, then do I have an equation that connects s and p together? I do, right? This is an equation. You see the two variables s and p in there? There you go. That's all you need. Any equation you could come up with that connects the two variables s and p together using similar triangles, I get an equation. Okay? So we have to know a little bit about similar triangles to be successful with this. All right, let's continue. I'm going to, let me do this. Let's clear the fractions out of here. Do you want to clear fractions? I don't even know. Let's cross multiply. I hate using that term, but let's do it. Let's multiply this here and this here to get rid of the fractions. And we will have this. We will have 6s equals then 20 times s minus and then 20 times p. And let's see, is this the same? 20p equals 14s, right? I just decided to move my s's to the right and move my p's to the left. So that way I could keep everything positive. Any questions on what I did there? Or is that an equation that relates s and p together? It came from here, right? It's the same equation, just written differently. So that's the one. This is the equation that I'm going to use right there. That looks like a very, very straightforward thing to take the derivative of. So my next step is implicit. I should tell you that on your test, your next test, the way that this is going to appear on the test is that I will probably give you 3 problems, maybe 4 problems, and have you choose 2. So I'm going to give you a variety of problems, and that way if you look at one, you're like, I have no idea, or something like that, you can move on to another one, and hopefully of the 4 I give you, you can do half of those. All right, so take the derivative now, right? And we're differentiating with respect to t, right? T. So the derivative of this, am I going to use product rule, or what am I going to do here? 20 is just attached, right? With multiplication, it can just come for the ride. So I bring the 20 down times, what is the derivative of p with respect to t? dp dt equals, here the 14 comes for the ride, And now the derivative of s with respect to t, which is ds dt. That's weird. Do we know dp dt? Yes. ds dt is what we're trying to solve for. Does anyone see anything interesting here?
It's on the right side.
Yeah, but this is like the snapshot, right? The moment in time. P is 12. There's no P in here, right? Which means what? What do you think that means? We're going to replace this with what? 7, right? Let's do it. Let's just replace it with 7. Replace that with 7. 20 times 7 equals 14 ds dt, right? And then divide by, I think we get 10, right? Is that right? We should get 10 ds dt. Pretty sure. Because you multiply these two together, what do you get? 140? Divide by 14, you get 10. This is our answer. It's measured in feet per second because s is measured in feet, t is measured in seconds, 10 feet per second. But I want you all to see something that I don't think anyone has seen yet. Exactly. The P, in this differentiation, the P never appeared, right? Which means this P has no impact on the speed of the shadow. That means his position, the position of the man, has no impact on the speed of the shadow, where he is. The speed of the shadow is always what? 10 feet per second, regardless of his position. Which means if he's running or walking fast at 7 feet per second, his shadow is moving at 10 feet per second. But that's a constant speed, right? It's a constant speed. Just like he's moving at a constant speed, the shadow's moving at a constant speed, but the shadow's moving faster than him, so it looks like it's moving away from him, right? It's like if you're running behind someone and they're running faster than you, they're gonna move away from you. That's exactly what's happening here. But his position doesn't matter. The shadow's always moving at 10 feet per second. I'm not quite sure if how that plays out in your mind, if that seems like that's intuitive or not. I think for me, this is counterintuitive. I would think that his shadow is speeding up and getting faster and faster and faster, because I imagine him being like really far away and his shadow being like huge. But it turns out that his shadow is moving at a constant rate. And the only reason we know that is because his position is irrelevant in this formula, right? His position does not impact this at all. Now, had this had a P in here, had there been a P in there, then of course his position would matter, right? It would change that answer. Okay. We have 20 minutes, not enough time to move to the next section, but enough time to do one more of these perhaps. This is it though. This is the last example I'm going to do of related rates. Then you're going to have your homework problems to do. And remember, I've got my videos on the homework, so try and do them on your own. Don't just watch me do them, okay? A conical cup is 4 inches tall, 6 inches wide. So it's something like this, like a paper cone cup, right? Something like that. It's 4 inches tall and 6 inches wide. Water is being poured into the cup at a constant rate of 2 pi cubic inches per second. So we're pouring water into this cup at a constant rate. How fast is the water level rising when the water is 1 inch from the top of the cup? So if I start pouring water in here, the water level comes up. In the beginning, that water level should be coming up pretty fast, right? But as I get further up, it's going to slow down because it's widening out, right? Do y'all see that happening if I'm pouring at a constant rate? I will show the animation of this one. So I'm pouring it at a constant rate. It's really slow. Like I'm pouring it at a constant rate, but it's slow because the cup is widening. When this starts over, watch how fast the water level comes up in the beginning. Okay, here we go. Right there. See how fast it came up? It's because it's narrowed down to a point there, right? So it's going to fill that volume up quickly, but as the cone widens out, it's going to take longer to come up, right? So we want to know at exactly that moment, boom, when it's 1 inch from the top, I want to know how fast that water is coming up the side of the cup, right? This is related to that problem with like a dam overflowing, right? You're trying to figure out like how fast is that water coming up at a specific moment in time. All right, everyone understand the picture? All right, let's get a picture going. We got 20 minutes, less than 20 minutes. All right, so my general picture, a cone, not drawn to scale. Now, this cone does not change, all right? It is 4 inches tall, and it is 6 inches wide. I know that doesn't look like 4 inches and 6 inches, but let's just say that's what it is, right? That doesn't change. I mean, that is, the cone is the cone. Now, inside the cone, I have water, right? That's a different thing. That's changing. So inside of here, I'm going to put my red blood water in here like this. Okay, and that water level is, you know, at different places at different points in time. That's my general picture. At the instant in time, I have the same conical cup, right? This is still 6. This is still 4. But now I actually know where my water level is, right? Where is it? 1 inch from the top. 1 inch from the top. Remember, the cone's 4 inches, right? So the water level here is 1 inch right there, right? 1 inch right there. That's a 1. All right. What am I given? What do I want?
Given the rate in which the cup is filled.
Okay, which would be a measurement of what? Like when you have your jug, right? You fill that with water, right? That is a measurement of a what? Is it volume, right? It's a volume, right? We know how fast the volume is changing. We're pouring in at a certain rate, right? The rate that we're pouring in is 2 pi cubic inches a second. That is the change in volume every second, right? Change in volume. So that's what I'm given, right? I'm given the change in volume with respect to time to be 2 pi, which is weird, cubic inches per second. Now, V, volume, is not labeled on my pictures, right? It's not labeled here. Like there's no V labeled because V is not a length of a side or anything like that, right? V is the volume of the red part, right? The volume of the water is the V. So I'm given how fast it's filling up, What do I want? The speed at which what? Water's rising. My water level. Do I have that labeled? My water level? Do I have it labeled anywhere? This is 4, right? That's the cone, not the water. We're talking about the water, right? Do we know, have we labeled this height? No, so we should probably call it h for height, yeah? Why don't we call this distance from here to here, why don't we call that height? So I want to know how fast that height's changing, right? I want to know what's dh dt at the moment what? That it's 1 inch from the top. Is there another way I could say that?
H equals 3.
H is 3, right? In other words, if the cup's only 4 inches tall, then 1 inch from the top would mean that the height of the water is 3. The key variable in this problem right here is the V. We have to find a way to connect V and H together right now, right? Where V is what? The volume of the water. Not the volume of the cup, the volume of the water. Right? So let's talk about, let's just take a little time out here. Let's see, can we figure out what the volume of the water is? Just looking at this right here, this volume right here, if I give you a little cone like this, okay, what is the volume of that?
It's 1/3 squared.
1/3 pi r squared h, where h is the height of that water and r is the radius of that water piece, the radius of the cone, right? That came off your formula sheet, right? So that is the volume of any cone. And we're talking, again, we're not talking about the cup cone, we're talking about the water. So we're trying to find a formula that connects V to H, right? V to H. Do we have a formula connecting V and H together? Does this V represent the volume of the water? Yes? Does the H here represent the height of the water just like it is over here? Yes. So this does connect V and H, but what's the problem? The R, right? That formula requires that we know R. Do we know R? No, I'm going to cut you off before you say yes. Don't tell me the radius is 3, because now you're talking about the cup. We're talking about the water. We're talking about the radius from here to here. That's a different radius, isn't it? So do we know it? No, not directly, right? So I don't want to differentiate this formula, because if I do differentiate it, I'm going to get a dV dt. Yes, I'm happy. I'm going to get a dH dt. Yes, I'm happy. But I'm also going to get a dr dt, which I know nothing about, right? I do not want to see that appear. So this is the first problem we've had where we really have no other formula other than that. And we need to find a way to make this R not be a problem, all right? We need to somehow get rid of the R. Somehow, all right? So this is the first time you're seeing this problem, so I'm just going to show it to you. This is kind of cool. It's kind of tricky, though. What we're going to do is we're going to take this scenario right here, see the cup, and you see the water in it? We're going to come through with a magic sword, and we're just going to slice it right in half, okay? I'm going to cut this in half, and we're going to look at what's called a cross-section. If I look at that cross-section, I've cut that cone. I now have this shape right there. And then my water level would look like that, wouldn't it? So we've cut the cone in half, and now what you're looking at from cross-section, you open it up. Of course, the water's not pouring out because this is like a magical sword, right? Everything's frozen there. If you look at this, now you have triangles, right? And if I drop right from the middle, let me go up like this. If I do that, now let's just look at one side of this. I'm going to label it like this. There's my water. Do you all agree that the distance from here to here is h? From there to there, that's h. Do you all agree the distance from here to here is the r that we're referring to in that formula? Right? Like this r right here is that r. Now, finally, the cup dimensions can come in. Do you all agree the distance from here to here is 4? And the distance from here to here is 3. Right? What have I done here? What have I created here? Similar triangles again, right? This is another set of similar triangles. Do y'all see the red triangle and the black triangle? Red and black. Let me draw them side by side. Here's the black one. 4 and 3, right angle. Here's the red one. H and R. Right? They both have the same 90-degree angle here. And they both share this angle right there. They both have that same angle. So these two angles are the same. And that means that those two are the same. And therefore they're similar triangles. And if they're similar triangles, then the ratio of any sides are equal. Ratio of congruent sides are equal. That's not a very natural thing to want to do on this problem, right? To just straight away go and start slicing things in half and looking at these ratios, but that's the way you do it. I mean, there might be some other ways, but this is probably the quickest way there. Don't lose sight of the goal here. We were trying to come up with an equation for V and H to connect, but we had an R in here that we didn't want. So what I'm doing with this is I'm going to use this to create a relationship between R and H, and then I'm going to go back into that formula and replace that R with this new relationship. Is there a question? Yes, in this one.
And then
That's this cut in half, right? When I cut this in half, sorry, this is 6, right? And this is 4 when we cut it like this. But then I'm only taking half of this, so that's 3. Is that what you're asking?
I'm kind of trying to figure out, like, both of the triangles right there in the middle.
Uh-huh.
Is one of them supposed to be our given, and is one of them supposed to be our instant? Like
No.
after we draw that in the
Nope.
equation, they're both just one.
This is all still just in the general picture. I'm not looking at this at all until I differentiate some equation. Then I'll come look at this. Right now I'm working purely off of this picture right here, which is why I left this as H. And if this is H, I don't know what that R is, right? I don't know what it is. So from here, let me create from the similar triangles. Let me do this. I'm going to do this the H divided by 4 must be equal to the R divided by 3. Do you all agree that I can do this because these are similar triangles? I can take the longer side here divided by the longer side here, and the shorter side here divided by the shorter side there. And now one more thing. I'm going to take this and solve for R. Why am I solving for R? Because I'm going to plug it right in here. Solve this for R. Multiply both sides by 3. You get 3/4 H equals R. The radius is always 3/4 the height. That's what that's saying, right? If you have this particular cone that's 4 inches tall and 6 inches wide, then your radius is always 3/4 your height. And now I come back to this formula right here, and I'm going to plug things in. So my volume is now 1/3 pi. My radius is not going to be written as R anymore. It's going to be written as 3/4 H. That's the radius squared times H. Right? So I've replaced the R with something that has H in it instead. Now everything has H. So I have V and H connected with no other extraneous variables that cause a problem. I'm not going to differentiate yet. Well, let me do it this way. So here I just squared this, right? I square the 3/4, I square the H. And I put everything together now. I haven't done it. I'm not taking derivative here, right? I'm just cleaning up. 3/16 pi, that's just all this stuff cleaned up, times H cubed. This is the volume formula connecting V and H together for this particular cone in this particular problem. Who has questions? We're almost out of time. Anyone have a question where I got any of that? Yeah, H, because you have that H on the outside there waiting to be multiplied. So now I can differentiate this, right? Let's do a quick derivative. I only have 2 minutes. Let's do a quick derivative here. The derivative on the left side, I'm differentiating with respect to t. Derivative of the left side is dv dt, which I'm happy to see because that's actually 2 pi for us, isn't it? Right, remember dv dt was given to us, 2 pi? Equals, okay, over here, 3/16 pi, that's all a constant, isn't it? That's all a constant. So I'm just going to bring it with us. Times. Now, the derivative of h cubed with respect to t will be 3h squared, right? 3h squared, that's just your power rule, times, now your chain rule, derivative of h itself, dh dt. Follow? Any questions on that derivative? All right, I'll leave you the rest to finish because there's nothing else. You have everything, right? dv dt is what? 2 pi? What's h in the problem? Now we can fix everything. H is 3, right? So you're just going to put 3 squared there is 9. dh dt is what you're solving for. So just plug 3 in there, replace that with 2 pi, and then go solve for dh dt, and you will have the rate at which the height of that water is coming up that cone at the exact moment in time we're talking about. Okay. We move on after this into stuff that I'm sure you'll be welcoming with open arms because it won't be word problems anymore. But I highly encourage you to